Okay, so off we go. So let's see here. This is where we were last time. We were talking about the multivariable chain rule. Again, here it is. The big idea summarized very nicely right here, that what differentiation does is it turns a composition into a product, and in this case a product of matrices. Now let's walk through real quick to remind ourselves where this comes from. Oh, and let me click into full screen mode. There we go. So where does this come from? Well, it comes from this picture here. I guess I'll, there we go. So if we claim that this matrix and this matrix, product of matrices, but of course that is itself also a matrix. If we claim that this is that these two are equal, what I'm saying is that as applied to some vector, for example, let's take this x prime right here, they will always give the same result. And a pretty straight easy way to see this is just observe that, well, the derivative of f is what you do to the green vector to get y prime, and then that result, let's see here, colors, you apply the derivative of g to that to get z prime. Or alternatively, notice that you can just apply the derivative of the composition directly to get the exact same z prime. So therefore, these two matrices in purple have to be equal to each other, right? So that's all it is. It's not, ultimately, if you look at it from the point of view of matrices, it's not that deep. It's just, well, there it is. Right? Okay. All right, now there's a detail that I kind of glossed over in a rush last time that I want to hit now, and that is where do you evaluate these matrices? And I'm going to start off by pointing out that df is evaluated at the point A. Now, why is that? Well, because df is applied at the point where f is applied. F in this point, in this case, f is being evaluated at the point A, so df also evaluated at the point A. Okay, well, with that point of view in mind, now let's look at dg, and the thing about it is dg is evaluated, let's see here, dg evaluated at the same place where g is evaluated, and if we're talking about the scenario that we have set up here, g is evaluated at that point. That is not A, right? It's f of A. It's what came out of f from the point A. And so that's why we have to stick this in here. The DG matrix has to be evaluated f of A because that's the only thing that makes sense. Okay. All right. Okay, so now that we've got that done, let's sort of proceed along to see an example. And so here I have a bunch of setup. This is all just givens. So notice in this example, I'm not telling you the formula for either of these functions, right? So this is I'm going to give you limited information, and I want you to use the limited information to find the specific things that the question's interested in. So we have composition of functions. You'll notice what comes out of f is what then subsequently goes in to g. Right? So f followed by g. In other words, we're going to be looking at the composition g composed f. And again, heads up, make sure you don't get those backwards. It's so easy to do, and it'll sting you real bad if you make that mistake. Again, School of Hard Knocks for me, hopefully better for you. Okay, so what are we going to do here? The question asks actually two things. The question is asking first to find this derivative matrix. We're going to focus on that part first. Secondly, it asks to compute a specific partial derivative. We'll come back to that. Okay, so focusing on how to compute the derivative of a composition, notice the very first thing I write down is just straight up recopy the chain rule. Multivariable matrix form of the chain rule. So I write that down. Again, that's immediate. Okay, so let's see here. Notice it says I need, apparently, df evaluated at the point 1, 2. Oh, cool. I was given df evaluated at the point 1, 2. I can just copy that down. Life is good. Okay. All right. Next thing that I'm going to need, again, you can see right here from the equation, I need dg evaluated at the point f of 1, 2. And awkwardly, that doesn't appear to be quite exactly what I was given. I was given dg evaluated at the point 3, 1, 0. And so this is where we have to use this other piece of information I was given, which is that f of 1, 2 is, in fact, 3, 1, 0. So, again, lucky break. Well, obviously the question had to be designed this way. I can't make it where you don't have enough information, right? But in fact, despite appearances, I'll say there, in fact, we were given exactly the matrix we need there as well. And then you just multiply them and we win. Is everybody happy with that first part of this? Okay. All right. Let's see, talking about order, again, I talked about, you have to be careful about not to accidentally reverse the order. On that same topic, I will point out, in fact, I'll just roll back here to where we originally wrote it down. Conveniently, the order of the composition in this notation is the same as the order of the matrices on the other side there. So that's nice, right? So as long as you get it from diagram to algebra correctly, you're good within the algebra. Okay. All right. Okay, second part of the question. So second part of the question says compute, let's see here, the partial of z3 with respect to x1. Now we have to think very carefully about what exactly are the interpretations we're going to make of the matrices that we have and the matrices the matrix that we just computed. So notice z3 is the third of the three output variables that I was given. Right? Remember, output variables correspond to rows. Right? So because I'm interested in the partial of the third output, right? Third output means I'm going to be looking in the third row, and there then is the row in which I will find what I'm looking for. Okay, but now wait a second. Further than that, we want the partial with respect to x1. x1, you will notice, is the first of two inputs. Inputs correspond to columns. So if I'm looking for the partial with respect to the first input, I need to look in the first column, namely that column. And so you can see all together then, the partial I'm looking for is that entry in the now identified row and now identified column, and therefore the answer is 3. Everybody on board? All right, let's see another example. I'm sorry, I got ahead of myself. We'll do another example down the road. Okay, so one special case. This is a real quickie little observation I want to make here. Here you will notice I have a composition of functions, and this is a special case I want to think about. The special case being that while the second function is vector valued, multivariable, and the first function is vector valued, it is not multivariable. Right? Notice there's only one original input variable. And that has a couple of consequences. Now, it does remain that the chain rule applies. Absolutely. The derivative of the composition is the product of the individual derivatives. That much is still true. Right? But here's the asterisk. Because there's only one input variable, t, right? Only one input variable. If you look at this first matrix, the derivative matrix of this first matrix, well, there's only one input variable. That means the derivative matrix will only have one column. Because again, you get a column for every input variable. Okay. Secondly, let's look at the composition. The composition gives the y variables in Rm as functions of, again, just one variable. So one input. So its derivative matrix, having as it has only one input variable, also has only one column. All right. So now what does this mean? I mean, how do I interpret this? I would point out that if you have position x or y in Rn or Rm, whatever, whichever one of these functions you're looking at position as a function of time. These two functions, the blue one and the orange one, are parametric curves. And what we're looking at here with their derivative matrices, as we've already noticed previously, yesterday, these derivative matrices are actually just velocity vectors, right? So what I get all together then is I can make an interpretation about the derivative of the of this f function right here. The derivative of that f function is going to take my, oh gosh, I've already forgotten what colors I was just using. Okay, blue and orange. Okay, so it's going to take my velocity vector, x prime, whatever is my velocity vector in Rn, and it's going to multiply by that to give me, as a result, the corresponding velocity vector in Rm. So what this is old news. This is a recovery. This is a reminder that, as we already discussed, this is what derivative matrices do. Derivative matrices turn input velocities and output velocities. So I just kind of like making this observation that the chain rule, at least this special case of the chain rule, can be viewed as just a sort of a refresher, reminder, reinterpretation of what derivative matrices are. Right? So pretty natural. And I like it when we kind of connect dots like this. Okay. So I have an example here. I'm going to go super quick through the example because all this example does is demonstrate the fact that we were just reminded of, which we've already talked about. So this is a redo kind of a thing. But here, notice I have a function from one space into another space. And the question is about if I'm moving with some sort of an input velocity to determine, as a result, what is my output velocity. So how do you relate input velocities to output velocities? Well, derivative matrix. So you compute the derivative matrix, you plug in the point in question, and that resulting matrix is what you multiply by input velocity to get output velocity. It's all it is, right? Now there's details in there. It'd be a good exercise for you all to make sure that you're very crisply comfortable with how to take the appropriate partials of that f function, right? And that you can assemble them correctly to make sure that you can write down that original df matrix, and check through all the other little detail devils. What did you plug in? Why did you plug that in? Etc. Right? And I'm going to go ahead and assume that y'all are good at multiplying matrices. But anyway, obviously make sure you're good at that too. Okay, so this next special case is a special case of the special case, and there's very little to say about this one, actually. Remember, we just got through talking about the idea that if you have but a single input variable, call it t, let's say, then you're looking at a couple of, position as a function of time. You can interpret this, then the chain rule is a statement about velocities. All good. The only thing that's different here in this special case is that we also have but a single output variable. And that means that the output velocity then is just literally a rate of change. It's, I suppose you could say that's the rate of change of position y as a function of t, but position y is just a number, and so it's just the derivative, right? Single variable derivative. So that just makes the algebra look a little bit different. Of course, the this function right here, now I can argue having a single output variable means this derivative matrix has a single row. And therefore, just another slight twist, I can view this matrix multiplication as dot product with the gradient vector. And we've made that observation before, that a matrix is kind of a transposed dot product. Right? Really, ultimately a fact of linear algebra. I hope you all have seen that in your linear algebra classes. Okay, and again, the example is, I'm going to let y'all just read this one. It's very straight. It's the morally equivalent to the example we just talked through. It's just that the ultimate function that we're interested in here is real valued, not multiple coordinates, just a single output coordinate. And then, again, the other difference being that I use dot product with the gradient because I can. Not that I have to, but just because I can. Okay, details for y'all. Okay, so I am a big believer that this is the best way to think about the chain rule. Let me just get it all onto the page here. That this is the best way to think about the chain rule, that it's a statement about derivative matrices. A couple of reasons. First of all, that's what derivatives are. I mean, ultimately, deep down, fundamentally, cornerstone point of view of how you should think about what a derivative is, it's a matrix, right? The derivative matrix. Partial derivatives are a convenient little tool, but they're not really the point. So this is phrasing the statement about derivatives in terms of honest, actual derivatives. So that makes it a natural point of view. It's also very conveniently, very compact, right? It's pithy, as we discussed. There's an easy picture to draw. I think this is really the best way to think about it. That said, there are some situations where it's a little bulky, and we don't actually necessarily want to write that all down. And there is an alternative form of the chain rule that is very convenient in certain specific circumstances. So I'm going to introduce this idea of intermediate variables, but we're going to get to that by first recognizing that if we have a couple of functions, notice set up to be composed, because what comes out of f is what goes in to g. Right? So we turn the x's into y's, and then we turn the y's into z's. And you can write down the matrix form of the chain rule. Here it is. I have it, you'll notice, now sort of expanded out to show what the elements look like. And think it through, right? I mean, the first function to act has its partials acting first. Namely, of course, that means they're on the right, because that's how matrices multiply, right? And then the one that acts second is on the left. And then the composition's on the other side of the equation. And now let's just look at this matrix product and think about how would I compute this particular single element. Not the whole matrix. Sometimes you don't need the whole matrix. And if you don't need the whole matrix, you could be forgiven for not wanting to have to compute the whole matrix, right? So if you just want the one element, all right, well, it's a matrix multiplication, so I'm just going to identify what row is that element in that I want. And I'm going to take that corresponding row of the left matrix, and I'm going to identify what column the element that I want is in, and then take the corresponding column of the right matrix, and as per usual, we do the dot product, and the dot product consists of taking the entries in that row and pairwise multiplying them by the entries in this column and adding them up. That's just how a dot product works, right? So this computes for me this one element that I was interested in with a single little formula here. No matrix multiplication needed anymore because we've already multiplied out that matrix product. Is that cool? So, pretty easy to see where that comes from. So this is a nice alternative form. I'll tell you in a minute why we use the term intermediate variables. The first thing I want to do is I want to dispel a myth there's a, let me go back here real quick to there's the single variable form of the chain rule, and what a lot of people like to do with the single variable form of the chain rule is say, yeah, because these cancel. Right? You've seen that before, right? May have even done that before. It is pretty handy. It's one of these things which in single variable calculus, what I like to call kind of a victimless crime. You're always going to get a good answer on that. That's okay, right? But it's a little suspicious. So can we do that same kind of thing? Where am I? Can we do that same kind of thing here? And the answer is a very emphatic no. Absolutely not. Yeah, I know. I'm with you. Because look at what here's the temptation. It's tempting to say, okay, well, how about I'll cancel those, and then check it out. That is that, and that is that, and well, golly, I don't even need all of this stuff over here. That's we're already good with just that first term, right? Obviously wrong. Obviously, we need all those terms. After all, we've already agreed that the matrix, from this matrix point of view, that's what the chain rule is. And this is a symbolic, superficial, in fact, ultimately completely invalid argument involving a fake cancellation that doesn't actually work. So anyway, strong temptation. Now, step one, or point one on this is make sure not to step on that landmine. I've seen it happen a bunch of time on exams, and it's just, oh God, it's a tragedy anytime a student does that and just therefore writes down only this and forgets all of this, because then there's no evidence on the page of the student having any actual valid understanding of the chain rule, which of course would be the point of a question that involved the chain rule, right? So this is a catastrophic mistake to make on an exam. Okay, so I want y'all also, though, to understand why this doesn't work. It's not that, well, this doesn't work because we don't like the answer it gives. That's not an argument, right? Here's why it doesn't work. If you look at the definition of what I've written down here, right, I didn't define this as a actual thing, and I didn't define this as an actual thing. So when I write this as a fraction, it's not a fraction. It's a notation that's vaguely suggestive that I can think of this thing as behaving like a fraction in certain circumstances. And that's true, right? But it's not a fraction of well-defined independent things. So to be careful then, just to avoid misinterpretations, I'm going to go with the very simple statement, that is not a fraction. Right? And in particular, let's think about how different these two things are. This thing right here versus that thing right there. I claim that they are different. Let's start by thinking about the denominator one over here on the left. That's part of what I'm going to call a story. There's a calculation here of this left partial derivative. That computation involves setting up a scenario and making certain assumptions. There's a story going on there. We've got these z variables. They're functions of a bunch of different y variables. Partial derivative says, among other things, that I'm going to hold all of the other input variables constant. So if zi is a function of all the y's, that means I'm holding most of the y's constant, and then proceeding with some calculation. Okay, well now let's think about thinking about this one over here, and what can I say about this partial y1? Well, again, that's part of a story. I'm viewing y1 as a function of all the different x variables, and I'm going to hold certain x variables constant, fine, but I'm going to be changing xj xj is going to change. And as xj changes, I cannot just claim that these other functions that are dependent on xj will just remain constant. I just cannot do it. I cannot assert that those will be constant. So you can see and I think it's very stark here, that in these two different stories, right, they are completely separate stories, as evidenced by the fact that these variables are doing totally different things. So they're part of different scenarios. You can't just say that they're the same. It'd be like if on number 3 on the exam, if I use a variable x that you compute and find that on question 3 on the exam x is 2, and then on question 5 on the exam, if x comes up again, it's not the same x. You can't just say, oh yeah, x was 3 as per the earlier question on the test. It's a totally different story. Unrelated. Complete nonsense. You cannot cancel those. Doesn't work. Is everybody comfortable with that? Okay. Alrighty. So, so there is a nice way that you can think about this. I do think it's good to have intuition for where this comes from. Part of the reason for the need for this intuition I'm about to show you is that not always will the variables be set up like this. So when we apply this version of the chain rule, it's not always going to be in this form. The variables won't be x's and y's and z's numbered by subscripts like I have here. Right? So if you want to memorize it character for character, that's not going to work. It just doesn't. Right? Too many different scenarios. So here's the way I'd like you to think about it. If we're composing functions, and if the first function takes x's as the inputs and gives you y's as the outputs, and if the second function takes y's as the inputs and gives you z's as the outputs, right? And then if I ask, what is the partial of zi with respect to xj, we can kind of play through the story of the overall big picture story of what happens as xj changes. How does that cause changes in zi? Where do those changes come from? And easy first observation to make is that, look, if you change xj, that's going to cause y1 to change. And I'm going to represent this effect, right, so that this causality of xj's changes will cause y1's changes by that arrow that I'm drawing right there. And by the way, I can also tell you exactly how much y1 is going to change, because that partial derivative is the sort of the magnification factor. You know, how much xj's change is going to get magnified to become y1's change. But here's the thing, when y1 changes, as caused by xj's change, that change in y1 itself will contribute a change to zi. And I can tell you exactly how much of a difference that's going to make, because whatever the y1 change is, that's going to get magnified to become zi's change, but again, by a partial derivative. And now check out this first term up here. The first factor there, this second factor here. What we have all together, this is the total amount that xj's changes will propagate through y1 to contribute to zi's changes. So the amount that through this path, through this intermediate variable, we call it, the amount of the change in zi that goes through that path is just that term right there. And then you can make an analogous argument for all the other paths. So through y2, there will be a term here that'll account for the fact that that partial derivative magnifies changes, and then that partial derivative magnifies changes. And then likewise through y3 and through y4, etc. And then finally at the end through ym. Does that all make sense? Okay. All right. So just as a little bit of lingo, I'm very regularly going to refer to this as the y1 term, and I refer to this as the y1 term partly because you see a couple of y1s there and there, right? That's clear. But also because y1 is the intermediate variable that this path propagates through. I think it's pretty natural terminology, so I'll call that the y1 term. And basically then you get terms for each of these intermediate variables. Okay, so with this picture in mind, now again, you don't have to think of it this way, and for whatever it's worth, this is my second favorite way to think about the chain rule, right? My first favorite remains the matrix form, right? Because it's ultimately the simplest form. Notice I had to do a whole lot of talking to make this kind of makes sense. And notice the resulting equation is big and bulky and hard to motivate. And ultimately, I think this is less simple than the matrix form. We're talking about preferences here. But this is very easy to apply in particular circumstances. So let's look at this example now. And again, I have a composition of functions. You can see here I'm given f, which turns x's into y's, g, which turns y's into z's. I've been asked for a partial of z2, the second of the ultimate output variables, with respect to x2, the second of the original input variables. And so this is looking for a derivative of a composition. Okay, well, in order to make use of the idea of intermediate variables, we need to draw a picture. That's what this is right here. This picture represents that f is going to turn the x variables into the y variables. You can see it right there. And that g is then going to turn those y variables into the z variables. You can see that right there. And now we have the diagram that's sort of this example's version of the diagram that I worked on here. And now I can just start writing down terms, and just to be as convenient as possible, I'll just point out, well, we only have two intermediate variables. There's y1, so we're going to have the y1 term, which you see right there. Right? And then there's, let's see here, y2. Here's the y2 term, you can see right here. And there's your chain rule. Is everybody happy? And then detail. So, you do, of course, have to be able to compute the various partials. Just to be blunt about it, let's look at this one right here. Partial of y2 with respect to x2. Okay, well, y2, y2, you can see right here, y2 is that formula, and I want to take its partial with respect to x2, all right, which I see, by the way, right there, right? So what is the partial of that green y1 expression, that green y2 expression, partial with respect to x2, and it's clearly x1 squared, as I have right there, so, etc.
If we had to plug in or compute the derivative at a certain point, would you plug it in at the very end, basically?
Yeah. I like. That's right. Yep. It's just like in single variable. Yep. And as usual, if somehow if you end up with y's in your answer, then of course the values of the y's you can determine by way of these formulas from whatever original x's you were given. Yeah, totally. Yep. Right. Okay. Okay, so now a couple of related ideas I have to point out. I want to warn you very much against the idea of confusion of variables. I'm going to go super quickly through this first half of the page because this is straight up single variable calculus, which I know y'all already know. I know y'all are already experts with the single variable chain rule. And let me show you the fast and loose and wrong, therefore slightly dangerous, quickie take on this, which is with derivative of compositions, the product of the derivatives. Right? You can compute these derivatives. The derivative of g is 3x squared, and the derivative of f is 2x, and you get 6x cubed, which of course is wrong. And the reason we got a wrong answer is because this was, you can't, right? In fact, the whole point, one of the points anyway, is that the g prime has to be evaluated at the correct input point, and I didn't do that. It's one point of view on that, right? So being a little bit more careful here, I recognize that g prime is that. Namely, whatever you're going to plug into g prime is going to be 3 times whatever that thing was squared. Right? And since I'm plugging in f of x, and f of x is x squared, then it's really x squared, to which I have to compute 3 times that thing squared. Right, now, that's fine, and you can do it that way, and you get the correct answer, and I guess that's okay, but golly, that was awkward, and talking about the thing that, and that's sloppy, right? Undesirable. Surely we could agree on that. So let me show you the much easier way to avoid all of that awkwardness is just to don't confuse your variables. We should recognize right off the bat when this question came to me, it was set up in a way that's unnatural. It's not wrong. This is a perfectly reasonable way to define two functions f and g. But look, I want to compose those functions, and if I'm going to compose them, then the thing that comes out of f has to be the thing that goes into g. And as it stands, that's not how it's written down, right? As it stands, do I have y as the thing that goes into the g function? No, I don't. Right now I've written g also in terms of x, which doesn't make any sense. X is way over there on the left. X is not what I'm plugging into g. I just straight up confused my variables through all of that, and that's just highly undesirable. So, look, this is easy to fix. There's nothing to it to fix. All you got to do is just say, look, we really need to rewrite g in terms of y, because y is what we're calling the output from f. And so let's just rewrite g in terms of y. And notice, rewriting this as that, super easy to do. I didn't do anything. I just used a different dummy variable. Right? That's the same exact function g, just written in terms of a different dummy variable. Is everybody okay with? Everybody see what I'm doing there? There's no problem. Yeah. So you do that, and all of a sudden, now life is good. Now because I'm not any longer confusing my variables, there's nothing to worry about. I can be as fast and loose as I want on how I write the chain rule, derivative of compositions, the product of the derivatives. Yeah, cool, fine. And I can be sloppy, careless about where I'm evaluating. Yeah, g prime is 3y squared, right? And let's see here, f prime is 2x, and then you just, kind of write that down and multiply, and then I get this nice little visual cue here that this result that I most immediately got for how to compute the derivative of the composition, well, the composition is written in terms of x. Let me say that differently. The composition is ultimately a function of x, so my answer should be written in terms of x. So I need to figure out how I'm going to get rid of this y, and yeah, no problem. Y is what comes out of the f function, so it's f of x. So there's absolutely no problem at all if you're just careful to don't confuse your variables. So I'm a big believer. Please keep this in mind when you're doing single variable chain rule. But of course we're doing multivariable, and so here's the multivariable version of ultimately the same thing. Notice I'm asked about a composition of a couple of functions that are both written in terms of the same input variables, and that's not good. And so just anticipating that, look, we're totally going to have a confusion of variables problem if we don't rewrite these functions, right? Well, let's just rewrite these functions. No problem. It's easy to do. F comes to me in terms of x and y. So what am I going to call its outputs? Well, I can't call its outputs x and y, right? So, okay, fine. Let's call its outputs, I don't know, u and v. And once I've decided that I'm going to call those outputs u and v, that means that needs to be what I write g in terms of. Okay. There you go. I didn't do anything there. I just rewrote g in terms of different dummy variables. Didn't change g a bit. Same exact function g. But now I have everything written in terms of unconfused variables. And now again, go crazy. Here it is again, fast and loose with the chain rule, derivative of compositions, product of derivatives. I don't have to worry about where I'm evaluating it. I've set it up to where that'll automatically solve itself. Right? So, you take this, let's see here, this g function that we have there, and you compute dg. And then you take this f function that we have right here, and you compute df. Just write it down. Nothing to worry about. And you can multiply that out right there. I am going to, in anticipation of potential algebra issues, go ahead and save myself the trouble and plug in now. And I'm going to have to figure out, for example, what to do with this u. What is that u? And I guess I'll point out that u is the first input to g, meaning that it is the first output from f. So u is x squared plus y squared. Just recopying. Got a nice, crisp, clear diagram to read where all the variables are placed in the appropriate locations and functions written without confusion of variables. It's just a recopy, right? And then likewise, what am I going to do with this v right there? Well, it's the first input to g, which means it's the first output from f, which means it's x squared minus y squared. Let me stick that right there. Good. Boom. We win. Everybody all right? Okay. All right. Okay, now there is a related warning. This is kind of a broader warning, and that is that one version of this is don't overinterpret this idea of looking at propagation of changes. This diagram that I've written down here, that I made arguments about how the arrows point and paths of changes and stuff like that. Yeah, but notice it remained that part of the diagram came from literally a function that I am literally composing with what there is, again, literally a function, right? So ultimately, this all comes out of very much the matrix form of the chain rule, which is about compositions of functions. Okay, so you have to keep that in mind, and when you're going to use this idea of intermediate variables and paths and stuff like that to kind of generate your chain rule as needed, you better make sure that you're talking about actually a composition of functions, and it has to make sense as a composition of functions. Each one of these, the variables have to be independent, right? The input variables to g here, for example, those input variables, y1 and y2, they're independent of each other. y2 is not a function of y1. It's not written in terms of y1, right? And notice, again, I've also avoided my confusion of variables. The variables that come out of the first function are exactly the variables that are the inputs to the second function. Okay. So let me show you what can go wrong if you kind of get a little too careless, and if you decide, for example, that maybe you'll just apply this idea of paths and propagations to, let's say, this diagram. Something like that. Maybe you have a question where the variables are just related as they come to you. They're related per this diagram, such as you see right here. Right now, notice in this example down here that we're going to look at, y1 is a function of x1 and x2. And let's see here, y2 is a function of x1 and x2. And let's see, now this is a weird one. z1 seems to be a function of x1, y1, and y2. So that's why I drew those lines like I did in that diagram. It's exactly what came to me in this example in the equation. And then just to be complete, z2 is a function of y1 and y2. Okay, so a diagram like this is perfectly plausible. This can come up. And now I'm going to ask a rhetorical question. How is it that this is a function of independent inputs? It comes to me, I've written it in my diagram as being a function of x1, y1, and y2. But what would it mean, for example, if I wanted to take the partial with respect to x1? Partial of z1 with respect to x1. Am I going to leave x1 as the variable and hold y1 and y2 constant? I can't do that. If I change x1, y1 changes. It is a function of x1. We have a nasty problem here. I don't really know what this means in this context. This does not, as written, does not come out of a composition of well-defined multivariable functions where the outs from the one are the ins to the next. This isn't it. So we're in new territory here. We cannot apply the matrix form of the chain rule as written, and therefore we can't apply any ideas that we got from the the matrix form of the chain rule to this situation here. So we're in trouble. Everybody see the problem? Okay. All right. So the fix here, and I'm not going to make a general version of this, but the fix is to recognize that, well, look, this x1, I need this variable x1 to help me understand how to define y1 and y2. I also need x1 to be an input to z1, but that's the whole problem. So what I'm going to do is I'm going to basically define a new variable right here. I'm going to call it x1 star. I think I just made a mess. x1 star. X1 star, the formula for it, it's just x1. Right? It's easy formula. But I'm going to view x1 star now as being a different variable, and having set that up as a different variable, well, now we're in, oh gosh, I didn't need to erase that. Now we're in business because, check it out, I have these variables are functions of those variables, and I have that these variables are functions of those variables. I have a composition of what I could absolutely interpret as meaningfully, reasonably composed multivariable functions, right? And now I've got the matrix form of the chain rule, and we're all good. And so that is what we're going to do down here in this example. We have fixed the problem by inserting that new variable. Here it is, x1 star. It is just it's just x1 in terms of how to compute it. But there you go. Now, one other rewrite I have to do as a result, of course, the whole point of this was so that I could reinterpret z1 now without having a variable problem. So I need to rewrite what had been x1, which I'm really not, I very importantly don't want to view z1 as coming out of x1 anymore, right? I need to rewrite z1 where I have x1 star in that place. Is that cool? And we're all good, and this becomes a boring question at this point. It's just, for example, if you want to compute, now again, this is the partial derivative that was all messed up and confusing as we had it previously set up, but now, nothing to it. I have three paths. There's the x1 star path, and then there's the y1 path, and then there's the y2 path. You write down those terms, nothing to it. Convenient. How do I compute that particular partial right there? x1 star with respect to x1. Well, that's a really easy partial derivative to compute. x1 star is x1, so that partial is just 1, which of course I don't even really have to write down as a factor. And life is good. Okay, so heads up, make sure not to commit any diagram crimes, and make sure that what you write down makes sense. Okay. All right. Okay, let's talk about second derivatives. A quick side note, this stuff here is not in the book, and I think that's a major oversight. Again, I know a lot of y'all are engineers. This course is aimed at engineers, so if you're not an engineer, well, you're in an engineer's class. And engineers are not that different from physicists, and I can tell you as a former second major in physics, I had to use stuff like this a lot, right? This was a big, one of the big tools that I used of multivariable calculus in physics problems, in a certain category of physics problems. So I think it's weird that it's not in the book. You'll notice on the content syllabus, it's in the column called included material. I've forgotten what I called it, second derivative chain rule or something like that. So anyway, this is important material, and it is part of the course, even though it's not in the book. Okay, so first thing I want to do here, just for the drama of it all, is I'm going to scratch this off. We're not going to look at this just yet. We'll come back and look at that momentarily. But for the moment, pretend like we don't know that. We haven't thought of that yet. Okay, so here we go. We have, we have z as a function of x and y. So indicated on my diagram. I remind you that r and theta are the usual polar coordinates. Now, when I write that down, what I mean is that x and y are functions of r and theta. That's how we think about polar coordinates, is that x and y are these convenient functions of r and theta. So indicated on my diagram, and you can see I'm composing. So I can, in effect, view z by composition as a function of r and theta. Right. And let's real quick write down the chain rule to compute first partial of z with respect to r. And there's the x term, and there's the y term, and easy sort of rewrites down here, because after all, you know the formula for x as a function of r, and you could straight up compute that partial derivative. X is r cosine theta, so the r partial is cosine theta. Likewise here, that is that. And then this is just a notational sort of option. I'm just going to rewrite these like those just because I can, and it's going to be convenient in just a moment. And Okay. All right. Now, next question. Suppose I want to compute the second partial of z with respect to r, which of course is the r partial of the r partial. The r partial being something that we have in fact just computed there. All right. So that's sort of the first step in computing the second partial of z with respect to r, and I'm going to proceed with a quickie argument, and that is, now let's think very carefully about this. If I'm taking a partial with respect to r, there's r. Partial derivative means that the other variables at that stage are to be held constant. That means that theta is to be understood to be a constant because I'm taking the r partial. Well, if theta is constant, that means cosine theta is a constant, and likewise that sine theta is a constant. And so keeping in mind that for our purposes, as I take this r partial, sine theta and cosine theta, they're just constants, right? So I can very nicely factor out those constants like I've done here. And that was a lucky break. That part of our expression just happened to be a constant. And I'll point out, you won't always get that lucky. Sometimes it's a little annoying, right? But this is actually a product, and sometimes you have to write down the product rule. It just gives you more terms. Okay. All right, so proceeding along. How am I going to make sense out of this? And here's where a lot of students mess up. This is a really common mistake to make. Please don't let this be you. What a lot of students do, they look on here and they're like, well, I don't really see zx on that diagram. So, well, wait a second, though. I mean, I can just rewrite this, surely, as second partial of z with respect to r with respect to x, otherwise known as zxr. I missed my... Right, so why can't I just do that? Can I rewrite this as zxr? And I claim that no, you absolutely cannot. You can't, because if you try to do that, what you'd be saying is that you're viewing z as being directly a function of all four of these variables all at the same time, and those are not independent. X, among other things, is a function of r. And so that doesn't make any sense. I don't know what that means. That's not a thing, right? That's one of our rules back here, is that the input variables have to be independent of each other. So this is just wrong. And let me put a big X. You cannot interpret z as a function of four independent input variables because they are not independent. So this is garbage. Is that everybody clear on that? You just cannot do that. Okay. All right. So how do we fix this? There's a really easy way, as it turns out, to fix this. Let me get rid of all this trash. The way to fix it is to just recognize, as I wrote up here at the very top, if z is a function of x and y, then so are its partials. So zx is a function of x and y. If zx is a function of x and y, well, let's just put that on our diagram. Let's just directly indicate, in the same way that z is a function of x and y. All right, well, yeah, but zx is also a function of x and y. And likewise, zy is also a function of x and y. So So I'm just going to add them right onto my diagram, indicated as functions of what they are functions of. That's the big trick right there. Everything's all downhill from here. So let me pause on this and make sure everyone's comfortable with the idea of, ZX can be thought of as a variable. It is perfectly clear what it's a function of. Include it on your diagram. That's the thing that's going to make this all work. Details to follow, of course. Okay. All right. So now, how do I make sense of partial of ZX? There it is. With respect to R, okay, well, there's that. Hey, nothing to it. How do I make sense out of that partial derivative? Well, I have two paths. There's the x path through the x intermediate variable, thus giving rise to the x term. And then we also have, let's see here, the y intermediate variable through which we have through which we have a y path giving a y term. Those are the only two intermediate variables. Those are the only two paths, and thus these are the only two terms in the computation of this partial derivative. And so we've applied the chain rule. Yep.
Why are we saying x and y aren't dependent on theta?
They are. It's just that for the purposes of what we're doing here, we're considering a partial derivative with respect to r, and when you take a partial derivative, that means that the other variables in that stage are held constant.
So the diagram is specific to the question.
Oh, of course. Oh, yeah, absolutely. Yeah. Exactly. Yeah, and that's the main reason that you need the diagrams, because you always have to tailor it to the always different particulars and whatever question you might happen to be looking at.
Okay.
Yeah, totally. Yeah. How we doing? Is everybody with me? It's all over but the shouting. Let's just run it on into the end zone at this point. Let's see here, mixed metaphors. That's all right. Let's see. I need to know what is partial of ZX with respect to X. Well, there's nothing weird about that. That's just ZXX. There's no composition problem here. Z came as a function of X and Y. No intermediate variables. Those are totally independent inputs. I could just write down ZXX. There's nothing weird there. Yeah? Then there's stuff like this, partial of x with respect to r, again, easy trig. Y'all can check me on that. Let's see here, zy partial with respect to x. Again, that's zxy, nothing to it. Right? And then et cetera, et cetera. And it's all over except a little bit of algebra now, and you can multiply. You'll notice that these two kind of give you the same thing, and so you get 2 of that term, and then here's your ultimate answer down here. Everybody on board? I want to draw your attention to one other thing about how I wrote all this down. Here's another lesson that I learned in the School of Hard Knocks, and that is that when you have a lot to write down, right, like that's a lot, goes all the way across the page, right? It is easy, so easy to accidentally misinterpret your own writing. I've done it several times, right? And so take pity on yourself. Try to write things clearly, but also, and more to the point here, use space to allow yourself an easier time interpreting what you're doing. So you'll notice it leaps off the page very nicely here that what happened as I went from the one equation to the next is that all of this got turned into that. right? Because I spaced out what I have in blue here. I spaced it out to where this was directly above that, and these parentheses are right above each other. And so don't, a lot of people focus on, well, whatever, the next thing you write, you're going to put it in the very next little blank space on the page, and you don't want to get into this myopic point of view where you're writing, like a computer would or something, and just, always one thing next to the other. Make sure that you make it so that it is visually as apparent as possible as you're writing stuff down, what came from what and what part of the first equation turns into what part of the second equation. And I think this is a pretty good example of that right here. Okay. So again, it's not a mathematical point, but that is I think, really valuable strategic point on how to avoid making mistakes. Okay. All right. Now, reasonable next question. Who cares? Right? Always a good question when you're doing math. What's this good? What does this have to do with anything? And I have an example that I think is very persuasive. So this is what that looks like in spherical coordinates. So we're going to talk specifically, this is a real thing. This is called the Laplacian operator. It is bonkers important. It's necessary. If you want to talk about in the three-dimensional world that we live in, right? If you want to talk about how waves flow or how heat moves, how electrons behave, right? How's that for broad, applicable? Right? This is extremely important mathematical construction, and why this particular expression is so useful is, somebody else's problem. You'll see that in your physics classes, your engineering classes. Right. Okay, so how would you write that in spherical coordinates? And it very hard to see this coming, but turns out to be the case that if you, just like we did on the previous page, take a function that was originally written in terms of x's, y's, and z's, and if you were to then remind yourself that spherical coordinates means that x, y, and z are functions of rho, phi, and theta, and if you were to then start computing, for example, this second partial, the partial of f, second partial with respect to theta. Notice this is a chain rule, second derivative chain rule question. And if you were to go through arguments totally analogous to what we just did here, but with spherical instead of polar, you'd get some big ugly expression. And then if you were to do that same thing to compute that, and then the same thing to compute that, and et cetera, and if you combine all these things together, what you would find is that all of this turns exactly into this. So this method on the previous page is exactly what you need to be able to make the connection between these two expressions. Now, again, I hear the thoughts in the back of your head saying, why would I ever want to do that? Right? What a monster of inconvenience and ugliness. And I tell you what, I'm just going to stay away from all that spherical coordinate stuff because, my gosh, look how much easier it is in rectangular coordinates. Right? That's what I thought when I first saw this. And I was wrong. Let me show you why this is awesome. I claim this is actually super convenient. So here's a perfectly natural computation that you need to understand. So here's the Laplacian. That Laplacian participates, as you'll see here, in this equation, and this equation, by the way, did not come out of thin air. This is how you describe gravitational potentials and electric potentials, so very important. And if you're not interested in gravitational potentials and gravitational fields because you figure you're going to live your life on planet Earth, yeah, cool, right, okay, but electric potentials, very important. Right? In engineering, it's electric fields all over the place. Can't get away from it. Okay. All right, so very important equation. Here is a function that is very important to entertain as a candidate possible solution. to that equation called Laplace's equation. Why is this an important candidate? Because it works. Right? This is, in fact, what electric potentials look like for a single point charge. And likewise, again, if you might care, this is what gravitational potentials look like for a single point mass. Okay, so this is going to be a really important calculation. This equation now I can rewrite as the left side that I need to compute and for which I hope I will get 0. Okay, I can rewrite like this, or I can rewrite like this. Notice all I've done here is notice that my function f, I can write it in rectangular coordinates or I can write it in spherical coordinates. And my Laplacian that we talked about above, well, I can write it in rectangular coordinates or I can write it in spherical coordinates. And I'm quite sure at this point I still haven't made a sale, right? I know that you are looking at this and thinking, pass, right? Okay. Turns out this spherical calculation is way easier, like way easier than the rectangular calculation. This one I'm going to let you do on your own because it's not the worst thing in the world. I've survived having done this a few times in my life. Right? But it's inconvenient, and you can see there's a quotient, and there's a radical, and there's going to be fractions and second derivatives, and it gets a little hairy. It's doable, it's fine, but it's hairy. I'm going to walk you through this calculation. We're going to do it basically in our head. Here we go. Notice there are, in the operator that we're applying, there are 3 terms. Each of these 3 terms is going to apply separately to the function that we're applying to. So we'll take these one at a time. I will start with how does this first term apply. You see the very first cat out of the bag. I'm going to need to take the theta partial of an expression that has no thetas in it. 0, gone, done. There's no thetas in there. The theta partial is obviously 0. Likewise, how does this apply to that candidate function? Well, I'm going to be very first thing taking the phi partial of this expression that has no phi's in it. So 0, done. Yeah? Pretty nice, isn't it? I like it. Now we have to do ever so slightly a little bit of work on this last one because looking at how this applies to that, okay, fine. There is we're going to need to take the rho partial first of k over rho. Let's ignore the constants for just a moment because they're just factors. But the rho partial of 1 over rho is negative 1 over rho squared. Right? So constant, whatever. I'm going to have a constant over rho squared. That means that when I multiply by rho squared, altogether this is a constant. It's rho squared times constant over rho squared, leaving just constant. And then I take the rho partial of what I've just agreed is a constant and 0, and we walk away. We won, right? We got 0 for all 3 of these terms, and so nothing to it. Basically, at a glance, you can see that this is 0. So, big fan. Everybody on board? Okay. Oh, and I may be out of time here. I got a minute. Okay. But let me just do a little bit of previewing real quick. The first half of this page is just observations that we already know. So in particular, if you're looking at a real valued function, we are, for the purposes of section 2.6 here, we are going to consider only real valued functions. And if we ask, what do I know about a partial derivative? Well, I know several things about partial derivatives. On the one hand, it's a slope of a graph as you're moving in that certain direction. Right? It's also a multiplicative factor. It's what you multiply by input change to get output change. Right? Again, as you're moving in that certain direction. And now a couple of quickie references. These are exercises for you to think through. Well, this one anyway is an exercise for you to think through on your own. This is, in fact, just a different way to say how we defined partial derivative in the first place. And again, this is a good exercise, but notice this describes motion in the EI direction. And if you're moving just in the direction of one of the variables, then the other variables are staying constant as they're supposed to when you're taking a partial derivative. And really all this thing is altogether is this at the moment when t equals 0 is just a fancy way of saying I'm at the point A and I'm moving in the EI direction. And I'm interested in how fast the function is changing as I move in that direction. It's really just a rephrase of what a partial derivative is. And this over here is a rephrase of the chain rule, basically, as applied to this particular scenario. So what we're going to do next time is we're going to take these four facts, slope of the graph, multiplicative factor, this formula, these apply when you're talking about a partial derivative, and we're going to ask and answer, can we come up with an analogous kind of an idea where instead of moving along an axis, what if I'm moving at some random direction? What if I'm not moving along an axis? What if not all the variables are constant except for one? In other words, how can I generalize the idea of a partial derivative? And that's where we'll pick up next time. Okay, so I'm going to draw the line right there. See y'all. Golly, that's going to be Wednesday of next week when we finally get, because Monday is a holiday. Hope y'all have a good extended weekend. Tuesday is the exam. Don't have too good of an extended weekend, right? Got to do some studying, right? And then Wednesday we'll pick up from right here. Okay, have a good one. See ya. I'm sorry?
Tuesday is